Patricia Franco, CEO of VINCI Construction.
I'm Hui Song, the president of VINCI.
I'm Xiaoshen Gu, the market director.
I'm Daniel Game, the regional director of Asia.
I'm Gustavo Garcia, the regional director for Latin America.
Wilfredo Torres, the European regional director.
I'm Aldo Leon, regional director of North America.
And I'm Giovanni Bruschetta, the CFO.
And we're VINCI Construction Company. Recently, we are developing a project and we're going to present you our new productivity improvement study.
The area of study of this productivity improvement study is focusing on built-on-site piles. The process of this requires three equipments, which are a pile driver, a crawler crane, and an excavator. For this as well, it requires some material which include 3 tanks, Tremi tubes with its respective hopper, 5 water pumps, 1 tube of 12 feet long, box of bentonite, a bentonite mixer, and some minor materials. The crew needed for this activity is 1 pile driver operator, 1 crane operator, 1 excavator operator, 1 bentonite mixer, and 3 laborers. The project evaluated had 3 buildings near on site, 1 in the north, 1 on the east, and 1 in the southwest. In this site, the contractor did 184 piles of 135 feet long each pile, with a 3 feet of cross-section. Each pile had a 4,000 psi Tremi concrete. The process of built-on-site pile goes as follows. First, the topographer locates the pile and the bentonite starts pouring while the pile driver gets in position. Second, the pile driver begins drilling into the ground until it reaches its designed depth. Third, a tube of 12 feet is put on the surface to avoid crumbling of the ground, to later the reinforcement being placed and tied inside the pile. Fourth, the Tremi tubes are inserted inside the pile and it will go almost as deep as the total length of the pile to later connect with the hopper. And lastly, the concrete starts pouring until it fills the entire pile and the Tremi tube is extracted.
Hello, my name is Hui Song. I'm going to talk about the methods of study. First, I would like to introduce the crew balance chart. The crew balance chart was derived from a man-machine chart. It is a useful tool to analyze the sequences and durations of construction activities. It is a graphic technique which shows each person in a crew or machine element using vertical bars. These bars are to the scale of a time or progress measure. In our study, the crew has a drilling machine operator, a crane operator, a bentonite worker, and 3 laborers. This slide shows the records and analysis of 6 observations over the construction process we are focusing on. Based on the information collected and analysis, we created this crew balance chart. The different color represents different activities during the cycle of the whole process. In the crew balance chart, the individuals are listed across the x-axis. Each vertical bar is divided into sections, illustrating the time of a worker or a machine that is occupied for different activities following the working sequence. The vertical bars should include the whole cycle that consists of idle, ineffective, or non-productive time. Before creating a crew balance chart, these statistics related to time can be observed and recorded with the stopwatch method or more efficiently and concisely by taking time-lapse film. Particularly, color coding is often adopted in the crew balance chart to show specific forms of information, such as categories of activities. Using the crew balance chart, people can study the current working process and find out the interrelationships among the tasks. Then, the field staff can make adjustment of the task arrangement to reduce or eliminate the non-productive and non-effective time. Sometimes, the crew size may also be modified.
Hello, my name is Gustavo Garcia, and I'm going to continue with the presentation about the methods of study. The second method of study that we developed for this term project was the process chart. The main goal of the process chart is to analyze the sequence of the activities on the construction site. By using a process chart, we're able to analyze in a chronological order the sequence of the most important activities. As you can see in this table, in this diagram, the process chart uses symbols to communicate the action associated to each specific activity. It is important to match activities and actions because based on this matching process, we can identify the value-adding activities on our construction process. We can also identify waste in our construction site by mapping and matching activities to their specific action. For our TEM project, we analyzed and created a process chart for a cast in place pile element. We also identified the materials laydown area, and we saw that it could be modified in order to minimize the distance between the storage area and the construction area. The table shown is the original process chart. We decided to call it original because it is a process chart that we created before any optimization process was suggested. As you can see, there are several activities and locations that could be optimized. Finally, after the process chart, we decided to create a flow diagram, as the one that you can see here below, for the cast in place piles. As you can see in this figure, a flow diagram helps us to visualize the activities mentioned on the process chart. If we analyze the layout, we can conclude that some of the materials can be relocated in order to have a better work process and a safer construction site. It is interesting to review the flow diagram because sometimes when we are on site, it is complicated to identify safety hazards or waste. When creating a flow diagram, we can take a step back and analyze our process on a high level. The analysis will definitely help us to provide suggestions for continuous improvement.
The original crew balance chart considered one pile driver, one backhoe operator, one bentonite mixer, and 3 helpers. Using this crew and equipment, one concrete pile can be done in 255 minutes. However, the crew balance chart presented a considerable amount of idle time, which can be reduced by adjusting crews and equipment. 3 improvements were proposed for increasing the productivity of this activity. The first alternative considers 2 pile drivers, 1 backhoe operator, 1 bentonite mixer, and 6 helpers. In this operation, 2 piles are done in 255 minutes. Even though 3 more helpers and a pile driver were added to the operation, costs will be saved as we will be using the same backhoe and crane for erecting both piles, thus reducing their idle time. The value of the reduced idle time of the backhoe and the crane represent a higher expense than the addition of the helpers and the pile driver.
However, this operation will only work if enough concrete will be available for erecting 2 piles at the same time. Usually, for risk purposes, it is preferred to erect only 1 pile at a time. For this reason, a new alternative was proposed in which the same pile driver will erect 2 piles, one at a time. This alternative consists of 1 pile driver, 1 backhoe operator, 1 crane, 1 bentonite mixer, and 6 helpers. Using this crew and equipment, 2 piles can be erected in 270 minutes. The only difference between the original cycle and this alternative is the addition of 3 helpers. The idle time of the pile driver is completely eliminated. The pile driver is the costliest item in this operation, so reducing its idle time is the main goal. The additional cost reduced by the addition of helpers is minimum in comparison with the time and cost saved by the efficient use of the pile driver.
Nevertheless, it can be noticed that some helpers still have some idle time. For this reason, the last alternative analyzes the previous operation with a reduction of 1 helper. For this alternative, we consider 1 pile driver, 1 backhoe operator, 1 crane, 1 bentonite mixer, and 5 helpers. In this operation, 2 piles can be erected in 285 minutes. The reduction of 1 helper results in cost reduction, but the cycle time increases by 15 minutes. A cost analysis should be conducted to determine if the addition of 15 minutes to the cycle is less costly than keeping the 6th helper.
For cost, the team used RSMIN's 2015 as reference. The following tables show the cost of labor and equipment. The labor were pile driver operator, crane operator, backhoe operator, and helpers. The equipment used was an excavator, a pile driver, a crawler crane, and a backhoe loader. The original plan used one pile driver operator, one excavator operator, one crawler crane operator, one bentonite mixer, and 3 helpers. The hourly cost was $693.93. The productivity was 4.54 feet per man per hour, and the unit cost was $21.85 per square feet. For the first improvement plan, we had a pile driver and 3 helpers. Although the cost increased 5.5% to $732.53, the unit cost was reduced in a 47% to $11.53. The second alternative was just add 3 helpers from the original plan. The result was that the unit cost was $12.04. In the third improvement plan, the difference was adding 2 helpers to have only 5 in total. The result was a cost of $712.72 and a unit cost of $12.53 per square feet.